we introduced quantum states, but this course is special in the sense that we don't only care about quantum computers that are idealized, but we also talk about quantum computers which we have today. And to talk about noise and how it affects quantum states, we have to introduce a bit more notation. So we are going to talk about mixed states which factor in noise that affects quantum computers. So we talked about cats, which represent a quantum state. Technically speaking, this is called a pure quantum state. And we can introduce an entirely equivalent notation where we create something called a density matrix, which is a cat and the bra of this quantum state. And we can rewrite every single operation that we would otherwise do in a cat in this formalism. For instance, to get the probability of the outcome 0, we would write this. So we apply the same projection as we applied in a cat, but this time we apply it on this row density matrix. And instead of the length, the norm of this vector, we take the trace of this matrix. So we apply this matrix on this matrix. The outcome is a matrix, and we calculate the trace of it, which is the sum of its diagonal elements. So why do we need these density matrices? Why do we need this alternative formalism? Well, the reason is because we can also create probabilistic mixtures over pure states. So now you can have the same cat and bra description of a pure quantum state, but you can create a classical probability distribution over them. So this is classical ignorance. This is something that we don't know about the underlying quantum system. So, and if we use this formalism, now we can introduce noise and start making these noisy, imperfect quantum states. And to illustrate the difference, think about this cat, which is the equal superposition of 0 and 1. If we write out the vector form, this is just 1 over square root 2 in both elements. And if we write the corresponding row, then it will have 1/2 for every element in the matrix. On the other hand, if we create the uniform distribution over the density matrix corresponding to the 0 cat and the density matrix corresponding to the 1 cat, well, this density matrix will be different. It will not have off-diagonal elements. So these off-diagonal elements are critical for many quantum operations. These are sometimes also called coherences. And as you can see, this density matrix does not have any of these, and the diagonal elements are also equal. So this is not just a mixed state, this is called a maximally mixed state. And the maximally mixed state is the equivalent of a uniform distribution in classical probability theory. This means that we have absolutely no predictive power of what's going to happen next. So in that sense, the entropy of this state is maximal. So ideally, we want quantum states with a high coherence, but in reality, noise affects and these coherences disappear. So let's take a detour and let's take a look at what happens when we measure individual qubits in a multi-qubit system. So imagine that we have the maximally entangled state over 2 qubits, which is written in this form. And we measure the 0 qubit, which is, according to our notation or convention, is the rightmost qubit. So if we measure this and we get the outcome 0, we model it in this form. So this is the measurement operator, just the projection to the first basis vector. And we are not doing anything on this qubit, and we model it by applying the identity matrix on it. So in this case, this is just 2 by 2, this form. This means that we are not doing anything on the qubit. And we apply this on this state. So the state collapses from the superposition, and then you get this outcome. So now if you measure this state again, but now in the other qubit, you would get 0 deterministically. So this is an entangled state. It exhibits this very strong form of correlation. So even though you just measure 1/2, whether you get 0 or 1, if you measure the other one, it will be already determined. So let's take a look at what happens if you're interested in the marginal probability. So this state is like a probability distribution of 2 random variables, and if you know that we have a multivariate probability distribution, we can marginalize out one of our random variables. We can do the exact same thing in a quantum system by using something called a partial trace. So imagine that we write our maximally entangled state as a density matrix. You see that it has strong coherences here, although it's full of zeros, that doesn't matter. And the way we define partial trace is that imagine that if you have any matrix, here I have a 4x4 matrix, and you trace out some subpart of it, that the operation is defined here as this. So there are elements that you completely get rid of. These correspond to the random variable that you marginalize out, and then you sum these corresponding diagonal elements to get the final output. So this is the equivalent of marginalizing out a probability distribution. And if you apply this partial trace, say in the first qubit on our maximally entangled state, what you actually get is the maximally mixed state. This means that if we marginalize out on one of the qubits in this system, then we end up with a uniform distribution. We have absolutely no predictive power over what is going to happen in that on the remaining quantum system.